Let's take a look at the final review solution set for Chapter 7, which deals with exponential growth functions, the basics of logarithmic functions, and logarithmic function properties. We can see here the first example is looking at an exponential growth function. So, an exponential growth function is a function of the form y equals a times b to the power of x. And we learned that if our base is greater than 1, then that is an exponential growth function. And if our base is between 0 and 1, then that is an exponential decay function. In this case, our base is 4, so this is going to be an exponential growth function. Y equals 4 to the power of x, a very basic exponential growth function. We have our input-output values. Again, we can create ordered pairs based on our understanding of input-output relationships of functions, and we can plot those ordered pairs on a graph to express this function graphically. So we have our input values, which represent the exponent in the exponential function, and our output values represent the value that's created when our base is raised to that input value or that exponent. For example, y equals 4 to the power of x, and if our input value is -2, that is essentially asking what is the output when the input is -2. We see here y equals 4 to the -2nd power. We understand from our exponent rules that a negative exponent means that we take the reciprocal of the base, which is 1/4, and raise that to the positive version of the exponent. So this becomes 1/4 squared, or 1/16. That is where we get the output value of 1/16 from. 4 to the 1/2 power is the same as the square root of 4. Anything to the 1/2 power is the square root of that value. So the square root of 4 is 2. 4 to the power of 0 is 1. That is our 0 exponent property. Anything to the power of 0 is +1. And of course, 4 squared is 16. We can take those ordered pairs and those values and simply plot them on an xy coordinate plane. We can see here -2, 1/16. And as we will note, this exponential growth function will basically skim along the asymptote or the x-axis. It will approach 0, but it will never actually get to 0 in terms of its value. It will get smaller and smaller and smaller, 1/100th, 1,000th, 1,000,000th, 1,000,000,000th, etc. as the x value becomes less and less, but the output value will never reach 0. Then we get to the point where our exponents become positive, and here is where the exponential growth takes place. So we can see here when the exponent is 0, our output is 1, 0, 1, and then of course all of a sudden our input value or our exponent is 2 and our output is 16. So this is a classic exponential growth function graph. We can now take a look at the logarithmic functions and the properties of logarithms. So the basic logarithm model is here, and the basic exponential function model is here. Remember that exponential functions and logarithm functions are inverse functions. So that is their relationship. They are inverse functions. And we basically have the same components, the same pieces to the puzzle. So this says log base b of x equals y. if and only if the same base, b, raised to the power of y equals x. So we can see over here, no matter what the variables are, it is the relationship and the pattern that matters when we're dealing with logarithm functions and the partner exponential functions. So the answer to a logarithm is an exponent. So if we see here, rewrite the equation in exponential form, we are given the logarithm function, which says log base 7 of 343 equals 3. The answer to a logarithm is an exponent, so we know that our exponent is going to be 3. Our base stays the same, which is 7, and so that means in exponential form that is 7 to the power of 3 equals 343, which is mathematically correct. Again, we see here log base 1/5 of 25 equals -2. In exponential form, that is our base 1/5 to the power of -2 being equal to 25. And that is correct. We would take the reciprocal of the base when being raised to a negative exponent. So the reciprocal of 1/5 is 5/1 to the positive version of the exponent. So 5 squared would then equal 25. We can be asked to simply evaluate logarithmic expressions. Remember, the answer to a logarithm is an exponent. So when you are given the expression log base 9 of 729, what that is essentially asking is the base 9 raised to what exponent equals 729? And that can be expressed here. And that exponent is 3. So that is how we will evaluate this logarithm expression. For this example here, log base 8 of 1 equals 0. This is asking us base 8 raised to what power equals +1. And our exponent rules tell us that any base raised to the power of 0 equals 1. So essentially log base b of 1 equals 0. That is a classic logarithm model. No matter what the base is, if it's log base b of 1, it will equal 0 because any base raised to the power of 0 equals +1. In order to understand logarithms, we have to understand, obviously, all the pieces to the puzzle and how they fit together. So some of these example problems here test that knowledge. Log base x of 4096 equals 4. In this example, we are given the exponent, if you will. We are given the answer to a logarithm expression, and we are given the final value. We are asked then to understand what the base value equals. Another way to think about this is what base raised to the 4th power produces the value 4096. And in this case, that base value is 8. Here, we are given the base value and we are given the exponent. We are asked then to understand that relationship in terms of what value does that create when we take the base 8 and raise it to the 5th power. 8 to the 5th power equals 32,768. We learned that our calculators, our basic calculators, work with base 10, so logarithm base 10. So if you are given a logarithm expression and the base is not stated, like here, that the base is assumed to be 10. So this is essentially asking us, base 10, 10 raised to what power produces 2.54? Again, we can take this value and use our calculator to show that value. We can use our calculator and ask it log of 2.54 equals, and it will understand that it is going to show us the value that we would have to raise 10 to get 2.54. And that value, rounded to the nearest thousandth place as the directions ask for, is 0.405. Similarly, this is asking us for log of 3/4 or log of 0.75. Again, there is no base stated, so it is assumed that it is base 10, and this is essentially asking 10 raised to what power produces 0.75. Rounded to the nearest thousandths is negative 0.125. 10 raised to the negative 0.125 power produces 0.75 or 3/4. We can take a look at a word problem involving logarithms. One of the classic ways that logarithm expressions are used is in the Richter scale for measuring the magnitude of earthquakes. And it says here the Richter magnitude R is given by the model where E is the energy in kilowatt hours released by the earthquake. And we are given this equation. R, the Richter magnitude, is equal to 0.67 times the log of the value 0.37 times the energy plus 1.46. The question is, suppose an earthquake releases 15,500,000,000 kilowatt hours of energy. What is the earthquake's magnitude? So we are given the E variable here in the equation, and we are asked then to solve for the resulting R value, or the Richter magnitude. So we can set up our equation, and instead of then log of 0.37 times E, it is log of 0.37 times 15,500,000,000. That becomes log of 5,735,000,000. Again, if there is no base value here, it is assumed to be base 10, and we can use our regular calculator to calculate this value, this logarithm expression value here. This is essentially asking 10 raised to what power produces 5,735,000,000. Again, we can use our tool, our calculator, to figure out that value, that exponent, 10 raised to the 9.76 power, would produce this larger value. Order of operations tells us that we then multiply 0.67 times 9.76 to produce 6.54. Then we can add it to the final part of the equation, 1.46, to produce an R value of 8. So this tells us that if that much energy is produced, then this will result in a Richter magnitude of approximately 8 on the Richter scale. We also learned that much like exponents, logarithms also have specific properties, and these are some example problems involving a few of those properties. The first example here is log base 2 of 4 to the 5th power. We learned that we could expand 4 to the 5th power to a larger value and then simplify the logarithm from there. Or we learned that there is a pattern recognition involved with this type of model, which states that we can understand the exponent, in this case 5, can be moved in front of the logarithm expression, and we can be treated as a multiplication problem, which states 5 times log base 2 of 4 will result in that same value. In this case, log base 2 of 4 is 2, and 5 times 2 is 10. We also learned the product property of logarithm expressions, which states that a logarithm with the same base being added together is the same as a logarithm expression with that base, with those two values being the factors of a larger logarithm expression. In this case, log base 3 of 3 times 9 is the same as log base 3 of 3 plus log base 3 of 9. We can basically split up this logarithm expression. Log base 3 of 3 is equal to 1, and log base 3 of 9 is equal to 2. and obviously 1 plus 2 is equal to 3. We can prove this by understanding that if we just simply multiplied 3 times 9 to start the problem, we would have been left with log base 3 of 27. And 3 cubed is 27. So we can see that that model holds true, and we would get our same result here. We can take those properties and then expand them further. Again, we understand that we can take our exponent, in this case 4, and we can put it in front of the logarithm expression. So this becomes 4 times the log of 2 over 3. And then we can expand this because our quotient property, much like our product property in the previous example, states that we can understand that a logarithm expression of a fraction is the log of the numerator minus the log of the denominator. So log of 2/3 can also be split up and expressed as log of 2 minus log of 3. And this here can be the simplified version or the expanded version using the logarithm properties. Combining a few of these properties into one again, this problem here is log of 5 times x cubed times y times z squared. You can see here that this is the log of 1, 2, 3, 4 different terms being multiplied together. And much like the previous example here, where we can take these two terms, 3 and 9, and split them up as the sum of those logs, we can do the same thing here. And we can split this up and express it as the sum of 4 different logs because 4 different terms are being multiplied. In this case, we can also take the exponents, 3 and 2, and we can drop them in front of the log expressions there. So this becomes 3 times log of x and 2 times log of z respectively. And when we put it all together, we can see that this here is the expanded expression using the different logarithm properties.